Okay, so I hope I am audible. Yeah, the recording is taking place, and let me turn it full screen. All good evening, everyone. Uh, I am Shouharda Ghosh, a PhD scholar at the Department of Electrical Engineering, IIT Gandhinagar. I am taking the PMRF NPTEL sessions for the course on signals and systems in the version, and this is the Monday session for this course. And now we are significantly deep into this course, and we have already covered 50% of the course material, and we are in week 7. So what are the contents of week 7? So first of all, the Fourier transform in complex frequency domain is covered. Then we talk about Laplace transform, poles and zeros. Then in the concept of Laplace transform, we talk about an important concept, which is the region of convergence. Then we talk about Laplace analysis of LTI systems, and finally it concludes with Laplace analysis of RLC circuits. All right, so what is this all about? So till now, whatever discussion has taken place on signal analysis has taken place in the frequency domain or the spectral domain. So we had a signal x of t, and we used to take out its Fourier transform, which was x of omega, and if you go the opposite way, that's the inverse Fourier transform. So what happened was that x of omega, in other words, the signal xt is actually written as the sum of complex exponentials. Okay, sum of complex exponentials, and these are the corresponding weights or amplitudes of each of these basis functions. Okay, so the basis over here is the complex exponential, and we are using these exponentials to build up our signal. All right, and that is the basis. But then we found out that there were certain signals, not all signals can have their Fourier transform. So only those signals that satisfy the Dirichlet's conditions, only they have a valid Fourier transform. So although there are certain cases where you can use the you can violate this to a certain extent and then obtain the Fourier transform. I mean, we manipulate that to bring in certain fundamental signals, but in general, if you don't satisfy the Dirichlet's conditions, you won't be able to get the Fourier transform. So does that mean that our Fourier transform is not a complete package or a complete tool to analyze signals? Okay, So for example, you may have a signal of the form, say x of t equals e to the power 3t cosine of 2t. So if you look at this, so this is a signal which actually has an envelope like this, an exponential envelope, and then the signal keeps on oscillating or shooting up. Okay, so if you look at this, it does not satisfy this property that integral the area under the curve must be less than infinity. So such a signal does not have any valid Fourier transform, and hence what will happen, the thing that will happen is that you won't be analyze the spectral component of the signal. So we need something more general that will be able to characterize any signal. So when that happens, we use something called the Laplace transform. So what happens is that earlier in Fourier transform, our basis functions were complex exponentials, okay, e to the power j omega t. But in Laplace transform, which you should denote by LT, the bases are something else, e to the power st, where s is sigma plus j omega. So if you look at e to the power st, so it has two parts, e to the power sigma t and e to the power j omega t. So these two parts have two distinct roles to play. So e to the power sigma t tells whether the envelope of the signal, or we shall also use Laplace transform for systems also. So it talks about the envelope behavior, whether it is the series or the signal is diverging or converging. Okay, and e to the power j omega t talks about the oscillatory portion of our signal. So how rapidly or how slowly it is changing. So for example, if I give you can give you images corresponding to this. For example, diverging, you may have something like this, converging something like this. So like diverging for sigma greater than 0, converging for sigma less than 0, exponential damping. Oscillatory, if omega is very small, then you will have very slow changes, okay, omega small. And when you have omega very high, you have rapid fluctuations, omega large. So general signals you try to build up using okay, so e to the power sigma t e to the power into e to the power j omega t. Okay, so corresponding to this, we have something called the S plane, which is used to analyze such signals. So S plane has two parts, the real part of S, which is sigma, real part of S is sigma, and the imaginary part of S is omega. So it's sigma, we can write omega or j omega. Okay, so if you have any signal or something like this, so whenever we are dealing with real signals, they are always cosine or sine. So cosine and sine will always have a e to the power j omega t and e to the power minus j omega t term. Okay, so keep that in mind. So let's suppose I denote my signal behavior using these 2 points. So they have the same omega naught and minus omega naught, and this is sigma. Okay, so omega naught defines the frequency and sigma naught defines the envelope. You see sigma naught is greater than 0. So what will this green signal represent? So you will have an envelope like this, because e to the power sigma t is upwards. Alright, I think I should decrease the width. And now you have some omega naught, So based on that, my signal will vary like this. Okay, and now let me take another case where the red one denotes my signal. Alright, so in such a case, this is omega 1, this is minus omega 1, and this is minus sigma 1, where sigma 1 is greater than 0. So how will my signal look like? So if I draw the envelope, it's a decaying envelope because it's downwards. Okay, so you have the signal oscillating, and as it oscillates, its amplitude starts decreasing. Okay, then you can have another case where you see that the signal can have only this portion. Okay, only the real part is active and there is no omega part, no frequency part. So how will such a signal look like? So such a signal will be, it's minus sigma 2, so it will be a decaying exponential. Okay, there's no oscillation to it. The oscillation part omega is 0. Similarly, if I had I considered sigma 3 over here, it would have been something like this. Alright, and the farther it goes away, the higher is the rate of decay, as you can very well understand. Similarly, I can also draw corresponding to these, say omega 0 minus omega 0. So how will it look like? It will look like something like this, and if I choose some other frequency, omega 1 minus omega 1, as you can see omega 1 is less than omega naught, how will it look like? See, the variation is even slower. Okay, so I hope you have understood how, based on the location or a point that you take in the S plane, the corresponding signal will look like. So any signal that is in the left half of the S plane and this side is convergent in nature. Anything to the left of j omega plane is convergent, and anything to the right of this plane is the divergent. Okay, so then, but then what is this Laplace transform? The Laplace transform x of s for a signal x of t is defined as integral minus infinity to infinity x of t e to the power minus st dt. Okay, so but remember that this is a generic bilateral Laplace transform. So what I mean by this bilateral? Bilateral means that xt can exist between minus infinity to infinity, and if we have some condition where xt is causal. Now remember what I mean in causality, the signal can exist only after time 0. So in that case the limits start from 0, and this is actually called the unilateral Laplace transform. Okay, now the generic form of a Laplace transform, okay, let's say h of s, it is of the form Generally these Laplace transform that you will get are will be of polynomial forms or whatever. So it will be s minus z1, s minus z2, so on till s minus zn. Okay. Similarly, in a denominator you will have s minus p1, s minus p2, and s minus pn. In general, m is not equal to n. Now you see, for all k, h of zk is 0. Okay, see, be it z1, z2 or zm, all of them yield h of s to be 0, and these zk's are hence called zeros. Okay, these are called zeros. And if this h of s is the impulse response, we say that zk is the zero of the system. Okay, and now you also look for all these pk's. Now look, z and p, they can be either real or they can be imaginary or they can be complex also. Okay, so there's no restriction on that. p1, p2 and pn, h of tk is infinity. That means the value of h goes to plus infinity or minus. Acha, let me write this. It can be either of them, plus minus infinity. So these pk's are called the poles. And if you are finding if h of t is the impulse response and h of s is the impulse transfer function of the system. Okay, so if h of t is the impulse response of the system, then h of s is what we call the transfer function of the system. And we use this transfer function in the s domain to analyze the system in a much better way. In fact, we in the previous sessions we found the v out by v in of various circuits, and we analyzed their low pass high pass behavior. But let me tell you, this Laplace transform helps us in that analysis as well as other analysis as well. It will help us analyze the stability of various systems. Okay, and you will use this in even more detail in the control system courses. Okay, so as I told, z's are the zeros and these are the poles. Okay, and for any Laplace transform, let's say x of s or h of s. Okay, so these are not alone, they have an associated region of convergence. Now what is this region of convergence and how and why is it important? So let's say you have some x of s equals to, okay, so now let us take an example and show you why it's important to have this something called region of convergence. You look at the signal, x of t is e to the power minus at ut, and we assume that a is greater than 0. How does this signal look like? This signal looks something like this. Alright, x of t, this is t. Okay, now if you look at x of t equal to e to the power minus at ut, it's a causal signal and it's also stable. Okay, now let me try to find this Laplace transform. What will its Laplace transform be? X of s is minus infinity to infinity e to the power minus at ut e to the power minus st dt. Remember our formula, x of s equals minus infinity to infinity. This is the formula. Substituting this, Since you have ut, you start from 0, end at minus infinity, e to the power minus at, e to the power minus st dt, e to the power minus of s plus a t dt. Okay, so now let's look at this integral. Okay, this integral e to the power minus s is a variable here. Okay, now ask yourself, when does this integral converge? Think about it. The integral will actually converge if the s is, and moreover note that s is a complex number. Okay, so s can have a real part and imaginary part. So let me do that. 0 to infinity e to the power minus sigma plus j omega plus a t dt. Now for the integral to converge, what do I do? Let me take the real part in this absolute value, modulus e to the power minus of sigma plus a t, and I separate the minus j omega t. We know that this one has a magnitude of 1, so I can take that out, and I get e to the power minus sigma plus a t dt. Now see, sigma is a variable. What values of sigma can I choose so that this integral converges? You think e to the power minus kx integral 0 to infinity, this will converge if k is greater than 0. This converges if and only if k is greater than 0. Why? Because if k is greater than 0, then it will always be of this form. Okay, it will always be of converging, decaying form. Otherwise, if k is greater than or equal to 0, it will either be constant or it will start rising exponentially. And when you have rising exponential curves, their integrals are undefined. I mean, they blow up to infinity. So this converges when sigma plus a is greater than 0 or sigma is greater than minus a. Or how else can you write that? You can write this as real part of s is greater than minus a. And this is actually called the region of convergence. And how does the region of convergence look like? This is the real part of s, this is the imaginary part of s. This is minus a. Okay, so now real part of s, that means anywhere that is greater than minus a. So how will it look like? It will look like this. The ROC is the region that I am shading over here. This is your ROC. Okay, and one very important thing to note is that this ROC is right sided, that means it is covering the right half. And what does this right sidedness mean? The right sidedness means that the signal is causal. Okay, and you also see it includes the j omega axis or the imaginary axis. This one is the j omega, let me choose a brighter one. This is the j omega, oh sorry, this is too bright, too right. this is the j omega axis, and whenever you include the j omega axis, it means that your signal is stable. Okay, and okay, so what is the so we have found out the region of convergence, we have found out the properties, but we have not found out the Laplace transform. So let's complete that. So once we look over here, e to the power minus s plus a, assuming that s is in the region of convergence, so the denominator will have minus of s plus a, and you put your limits from 0 to infinity, and you get 1 upon s plus a. Okay, so what is it finally? E to the power minus at ut has a Laplace transform 1 upon s plus a, and the ROC is real part of s greater than minus a. Okay, I hope this is clear to you. Okay, now let me take a second signal. xt equals minus of e to the power minus at u of minus t. Alright, how does this signal look like? I'll follow everything in the same format so that things look similar. It's minus, so it will be on the flip side. So minus e to the power minus at will actually look like this. Okay, so e to the power minus at looks like this, hence minus e to the power minus at will look something like this. Okay, and when you have u of minus t, that means you are choosing all the values for t less than 0. U of minus t is the flipped version. The flipped version of u of t, you are choosing this thing, and 0 over here, this is u of minus t. Okay, so how will this look like? This will look something like this. Okay, this is how your x of t will behave. It is a downward going exponential. So what are the characteristics of the signal? The signal is anti-causal because the signal does not exist for t greater than 0, and the signal is unstable. Why? It's a growing exponential, so the integral will blow up to infinity. Okay, now let's find its Laplace transform once again. So the Laplace transform is x of s integral in this form e to the power minus at u of minus t e to the power minus st dt. Since we are doing from u of minus t, so the upper limit will go to 0, infinity e to the minus of e to the power of s plus a t dt. Okay, now so now let us do the integration directly, and then we will look into the region of convergence. So we integrate it minus s plus a t upon minus of s plus a 0 to minus infinity. This cancels, so you get 1 upon s plus a minus e to the power s plus a times infinity by s plus a. Now I assume that this dies down to 0, and we will see the values of s for which this dies down to 0, and then what we will get is again 1 upon s plus a. Look at this, isn't this very surprising? for the previous signal that looks completely different, you get 1 upon s plus a. You get, where did I get? Yeah, you got 1 upon s plus a over here. And now for a completely different looking signal over here that's anti-causal and unstable, you get the same Laplace transform. The Laplace transform is not unique, and that's the reason why we require the region of convergence. Okay, so you look at, now we shall look into the region of convergence. So how do you look at the region of convergence? Look at this. It's, if I slightly change the integrals, minus infinity to 0 minus e to the power minus of s plus a t dt. The integral over here is over the negative side of the t time axis. Okay, that's on the negative side of the time axis. So what do we need to ensure? Integral minus infinity to 0 mod of e to the power, let's directly let the sigma j omega goes outside, sigma at dt. Look at this. Now this is e to the power minus x. Now if e to the power minus kx, if I look for k greater than 0, it looks something like this. And over minus infinity to 0, this will always blow up to infinity. So k has to be less than 0, only then my integral will, my exponential will look like this, and I'll end up choosing this part from minus infinity to 0. So what does that mean? It means this k with sigma plus a must be less than 0. Otherwise, what does that mean? That means real part of s must be less than minus a. Okay, you look at this, the previous one, this one was real part of s greater than minus a. That was our region of convergence of the decaying slope, decaying exponential. And for the downward growing exponential, we have real part of s less than. Okay. So is the completely complementary or the opposite region of convergence? I mean, if I now try to draw it, and a is greater than 0, that's obvious. This is my a. And this is my region of convergence. Now look at this once again very carefully and compare it with the previous one. The previous one was right sided and included a j omega axis. This one, this ROC, is left sided, and this left sided makes it anti-causal. Okay, left sided makes it anti-causal, and the does not include the j omega axis. Look at this very carefully. The j omega axis, this is sigma and this is j omega. Is ROC does not include the j omega axis, and this makes it unstable. So finally, what do we have? E to the power minus of e to the power minus at u of minus t. That also gives me the Laplace transform 1 upon s plus a with ROC real part of s less than minus a. So you understand very well that this ROC actually helps us determine the complete signal, the nature of the signal, whether it's previously you just noted down just one thing, there's a only single pole, there's a pole at minus a. This signal also has a pole at minus a. Why? There's this 1 upon s plus a term. I hope you are able to see this 1 upon s plus a term, this becomes 0 whenever this s plus a becomes 0, that is s equals to minus a, that time the h of s or the Laplace transform blows up. So we call this a pole. Now both these signals have a pole at minus a, and whenever we have a pole we always denote that by a cross. So this is a pole at minus a and we shall denote that by a cross. Okay, pole at minus a and cross. But then you see over here what is the difference? The difference is in the region of convergence lying, one is lying in the left, that causes the signal to be anti-causal, and the other one has a ROC to the right, which causes the signal to be causal. And the other thing is that it includes the j omega axis, which makes the signal stable, and the other one excludes the j omega axis, which makes the signal unstable. This applies to systems actually, systems as well, so because you are looking at the impulse response. Okay, so now let us start solving questions. So the first question presented to us is, we have the signal x of t, that is e to the power minus 1 plus 2j t ut. We have to find its region of convergence. Okay, now there are multiple ways of solving it and I shall tell you one of them. Okay, find its ROC. It should not be the signal ROC, it should be find the ROC corresponding to its Laplace transform. Okay, now this is something that we have just now done. We remember in x of t is e to the power minus of at ut, its Laplace transform is 1 by s plus a, and the ROC is real part greater than minus a. In this question, a is a is 1 plus 2j, so your Laplace transform will be 1 by s plus 1 plus 2j. Okay, so how will my ROC look like? This is sigma, this is j omega, this is minus 1 and this is minus j2. So somewhere where these 2 points meet, here I will put my cross. Okay, now we can do the integration also. Okay, we can do the integration and then find the ROC, but then let me tell you something very simple. You have this signal over here, and ROC, if you can very well understand, is the real part thing, it plays with real parts. So ROCs in Laplace transforms are always strips, horizontal vertical strips. ROC in Laplace transform will be either vertical strips or vertical half planes. So when I mean vertical half plane, it is something like this, okay, and it's causal. You see, it's u of t, it's not u of minus t. So what will it be? It will be something like this, isn't it? This minus g of 2 doesn't matter. So actually the ROC should in fact be real part of S greater than real part of minus A. Real part of A actually. And so what does it turn out to be? It turns out to be real part of S greater than minus A only, minus 1. Okay, so the correct answer is real part of S greater than minus 1. As you can see very well over here, that this is the minus 1 plane and this is the half plane. Okay, now this is the vertical half plane, right side, right half plane. Okay, now let's look at the second question. You have the signal x of t equals e to the power minus 2t cos 3t ut. Find its ROC, find its Laplace transforms ROC. Okay, so now look at this. This is stable. Why does it look stable? You have e to the power minus 2t envelope and this cosine signal, and this is causal. So it's obvious it will be something of the form real part of S greater than something. So let me now do it in a different way so that you can into the integral form. Integral minus infinity to infinity xt e to the power minus st dt. Integral minus, this should be from 0 to infinity e to the power minus 2t cos 3t e to the power minus st dt, 0 to infinity e to the power minus 2t e to the power minus sigma t cos 3t e to the power minus j omega t dt. Now I take its modulo because I want to do its check its convergence. So it turns down to e to the power minus sigma plus 2, because this modulo maximum value will be 1, this modulo maximum value will be 1, sigma t. Now you see it's again back to the old form, and this happens when sigma plus 2 is greater than 0 or sigma greater than minus 2. So the ROC is real part of S greater than minus 2. Just hold on for some time. All right, fine. So I hope this one is also clear. So everything that matters in is the stability of the signal or the impulse response system. The system depends on the decaying, whether the slope or the whether the envelope is gradually decaying or it's rising. Okay, that so the ROC helps determine that. So this will also be looking the same, -2, and as always it will include the j omega axis. Now let's look at another question. How many different LTI systems can have the same transfer function Hs equals 1 upon s cube plus 3s square plus 2s. Okay, let's look at this question differently. We have a transfer function and we need to find the different number, how many possible LTI systems can we get from this single transfer function. Okay, and the hint lies in the ROC. Let's see, first let's try to break this h of s. H of s, if I factorize, so you see s is common in the denominator, so I take out s, I get s times s square plus 3s plus 2. Now this can be factorized very easily and you will get s times s plus 1 times s plus 2. So this is an all pole system. All pole meaning a system that only has poles, that has only poles and no finite zeros and only finite poles. The poles are s equal to 0, -1 and -2. Okay, so I individually equate them to 0 and I will get these values. Simple. So now let me draw the pole 0 plot for them. -2, -1 and 0. This is real part of s and this is imaginary part of s. Now we have 3 poles, and now what I had told you was that the ROC, region of convergence, are on the form of vertical strips, and a very important point of ROC is that ROCs never contain any pole. They can contain zeros. Okay, so that means that whenever you have a system with various poles, then you will have multiple ROCs. How? These poles, for example, let's say this system itself, I can draw these partitions. Okay, these are the partitions. Okay, each pole will create one single vertical partition. Okay, so for example, let me draw for the sake of explanation over here. Sorry. This is one pole, this is one pole, this is one pole, this is one pole. Okay, so each pole will create one vertical partition. These are the partition. This is a partition, and each partition thus formed is a region of convergence. This is one region of convergence, region 1. This is one region of convergence, ROC2. This, and why are these separate ROCs being formed? Because ROCs can never contain any pole, they can only contain zeros. This, another ROC. This one is yet another ROC, and finally we have another ROC. So you may remember I told you a few minutes back that ROC can be either vertical strips or vertical half planes. So when what I meant by vertical strips were these. This is a vertical strip, this is a vertical strip. I think I should highlight it. This is a vertical strip, this is a vertical strip, this is a vertical strip. These are half planes, these are extending to plus infinity and minus infinity. So one important thing is that we looked at the half planes where one goes all the way to the left. This is all the way left sided, so it will be corresponding to an anti-causal version of the signal. Okay, when it's 5 is right sided, and such corresponding impulse response or the signal will be causal. Okay, but 2, 3 and 4, these are finite strip. Okay, so when they are finite strip, what happens? In such cases our signal is non-causal. That means they exist in both sides. So what can be an example? So any signal like this, okay, both sides, anti-causal like this, causal like this, it can go up or down whatever way, but then by non-causal I mean that it will exist on both. T is t less than 0, then a signal, this is t greater than 0, and this is both. Okay, this and this, they will have their corresponding signals in both sided way. Okay, now so what happened over here? So in this case, this is a left half version, this is a middle strip, this is yet another middle strip, and this is a right half version. So you see there are 1, 2, 3 and 4. There are 4 ROCs. Okay, so in all the 4 ROC there are 4 ROCs, and hence corresponding to that you have 4 possible time domain response, and you will have 4 LTI systems. I hope that's clear to all. You have as many, depending on the number of poles you have, that will based on that you will create partition. You check the partitions, how many partitions are getting created, and then that many number of systems you have. And I mentioned the anti-causal and right-sidedness, and always remember that for stable system, j omega axis must be included in the ROC, but here you see neither 1, 2, 3, 4, 5, none of them have the j omega axis included in the sense that they don't lie exactly inside the ROC. So for all of them they will turn out to be unstable systems. Okay, good. Now this is question 3. Now let's move to question 4. It's a bit extension of the previous one, but it's a simpler version. So you have this signal or the system x of s, 1 upon s square plus 3s plus 2. We have to write all possible signals x of t. So indirectly what it is saying, it is asking us to find the ROCs, and corresponding to each ROC we then need to identify what kind of a signal we will get. Okay, so first let us try to decompose x of s. We factorize it, s plus 1 by s plus 2. Now you have to use the method of partial fractions, a by s plus 1, b by s plus 2. A will be limit s tends to minus 1. This is s plus 1, so s plus 1 equals to 0, s equals to minus 1. Limit s tends to minus 1, x of s times s plus 1, and that will turn out to be 1 upon s plus 2, and that's 1 upon 2 minus 1, and that's 1. B will be limit s tends to minus 2, x of s times s plus 2, that's 1 upon s plus 1, 1 upon minus 2 plus 1, and that's minus 1. Okay, so I would suggest you to go revise partial fraction decomposition techniques. So x of s can be written as 1 upon s plus 1 minus 1 upon s plus 2. Okay, I have broken this intentionally, and now I am not going to immediately convert them into Laplace. What I shall also write over here is that for 1 upon s plus a, real part of s greater than minus a will give you e to the power minus at ut, and for real part of s less than minus a, that means the others left hand side, we will get minus of e to the power minus at u of minus t. This is an important point to be used. Okay, now we have two poles, one at minus 1, one at minus 2. So you see there are three ROCs, ROC1, ROC2 and ROC3. Okay, let's look at one by one, look at them one by one. One, this is ROC, the first ROC. How can you write this first ROC? The first ROC is real part of s less than minus 2. Okay, real part of s less than minus 2. Okay, so we are considering everything to the left side. Now in this such a scenario, what will 1 plus s plus 1 look like? S plus 1 has a pole corresponding to minus 1. Okay, and you are taking real part of s less than minus 2, and if you consider this, it's a subset of real part of s less than minus 1. Real part of s minus 1 is one of the possible ROCs of this s plus 1 left sided. Now that will be satisfied only for this ROC. So 1 upon s plus 1, that is the negative side. Okay, it should be left side, it is the anti-causal part. So when it's the anti-causal part, what should we write? Minus e to the power minus t u of minus t. And 1 upon s plus 2, that's also the same, is the left side, anti-causal, minus e to the power minus 2t u of minus 2t. So what is x of t? X of t is 1 upon s plus 1 part minus e to the power minus t u of minus t plus e to the power minus 2t u of minus t. So you see the signal is left sided and unstable because it's e to the power minus t, e to the power minus 2t, both of them are getting added. Now let's look at ROC 2. ROC 2 is what? Minus 2 less than real part of s less than minus 1. What about 1 by s plus 1? This pole can have two ROCs, to the left of minus 1 and to the right of minus 1. So we are in this one, and the one that will support this is the left sided, that is the anti-causal version. So 1 by s plus 1's anti-causal version is chosen. Anti-causal version is this, and 1 upon s plus 2. Now we are to the right of this minus 2. We are to the right of minus 2. Okay. So now we'll choose the causal version. What is the causal version? E to the power minus 2t u of t. And then what will my x of t be? Minus e to the power minus t u of minus t plus minus e to the power minus 2t u of t. There's a minus t in u, there's a plus t in u, so it's both sided, and because of this e to the power minus t t u minus t, or you see this does not include the j omega axis. Because of this reason this is also unstable. The question that I'm discussing over here is very important from semester as well as exam perspective and interviews as well. ROC 3. What is ROC 3? It's to the right of minus 1, that's real part of s greater than minus 1. So 1 by s plus 1, what does it correspond to? It corresponds, the real part of s greater than minus 1 corresponds to the causal version, right sided version. So it will be e to the power minus t u of t. What about this? This is also far apart. This will also be to the right side. So e to the power minus 2t ut. So what will be x of t? X of t will be e to the power minus t u of t minus e to the power minus t u of t. Now you look at this. Both of them are causal. So it is causal, or you can also say, okay, I should have written this non-causal over here. I should have written anti-causal over here. And you see, it's both of them are decaying exponentials sum or difference. So this is stable, and this is also verified because j omega axis is included in the third ROC. Okay, so all that we have done has been summarized in question 4, 3, 2, 1. Small but very significant and important concept. Okay, the single ROC, because you will be able to find Laplace transforms of other lot of signals, but then it's even more important to understand the concept of ROC, because the same signal can have multiple ROCs. Sorry, the same single Laplace transform can have multiple possible ROCs, and based on that you will be able to get different signals. So that's a very important thing to keep in mind. Let's look at another question. Find the pole frequencies of the following circuit. So we have a resistor, an inductor, and then a capacitor. Okay, so we actually need to find the transfer function h of s, which is y of s upon x of s. So let me tell you, the R in Laplace domain remains R. The inductor, which was j omega L, if you remember in the Fourier domain, it becomes SL, and the capacitor becomes 1 upon SC. Okay, so we'll use the same technique, voltage division. So this corresponds to 1 upon SC, 1 upon SC, this corresponds to R plus SL. Now multiply both sides by SC. What do you get? 1 by S square LC plus SRC plus 1. Okay, so it's an all pole system. Once again, all the denominator is a quadratic equation. Let's look at this quadratic equation. S square LC plus SRC plus 1 equals 0. Now if I am to solve for this quadratic equation, what do we have? S equals to minus B plus minus root over B square minus 4 AC upon 2A. So we'll have two poles minus RC upon 2LC plus minus 1 upon 2LC R square C square 4LC R upon 2L 1 R square C square L square C square minus 4 LC by L square C square on 2L plus 1 upon 2 over R upon L whole square minus 4 upon LC. These are the poles of the given circuit. Okay, all right, so I think we have covered almost all the possible topics or concepts that were required, the important ones, and just few more questions for the sake of completeness. So this is question 5. Question 6, find the pole location of xt equals to sine 60 ut Okay, so let's do a general way. Xt equals to sine 80. Okay, now if I break that up, I get e to the power j sine 80 ut e to the power j 80 minus e to the power minus j 80 by 2j ut. Now I know e to the power 80 ut or a hat ut will have a Laplace transform of 1 upon s minus a hat. So I get x of s. Now I take each of these j a terms separately. 1 upon 2j times 1 by s minus ja minus 1 by s plus ja. 1 by 2j s minus ja s plus ja s plus ja minus s plus ja 2ja by s square plus a square a by s square plus a square. So sine 80 ut has a Laplace transform of a by s square plus a square, and I leave this to you as a homework. Cos 80 ut will also have Laplace transform as s by s square plus a square. You can easily do it by decomposing it into exponentials, as I had done it for the case of sine. Now you see, what was it? A is 6 over here because sine of 60 ut is what is being considered. So x of s is 6 by s square plus 6 square, and so the poles are at s equals to plus minus 6j. That's exactly over the imaginary axis, and imaginary axis means pure oscillations. The poles are at plus minus 6j. Okay, so I hope this you have been able to cover up every concept that I have mentioned over here. Thank you very much. I am closing the class for today. Thank you.